And hello, everyone. I believe this is my first time to give a talk in this community, and I am super excited to share one to few things with all of you. So for today, the main topic is asynchronous communication in serverless microservices. And I just want to quickly share with all of you about the story on how I structured this content and how we got here and talking about this topic. So my first encounter to asynchronous communication was more than 10 years ago when I was working in telco industry. So during that time, the SMS and MMS were a big hit. A lot of people use them. I believe it's simply because those are the only options, right? And talking about the messaging, there are three internal processes involved to send and receive SMS. There are MO, which is the message origination, MT, message termination, and DR, the delivery report. And all of these three processes require a very low latency. I still remember back then, the threshold was 200 milliseconds for client to get response back, and that's for any services. And beyond 200 milliseconds, it was considered as a bug, and there will be another change request coming in, and that means more work to do. And one of the models that I developed back then was the payment using SMS. This payment module needs to go through a few steps from authentication check for the request coming from the partners, and then validating the request, checking for sufficient balance, make sure there's no double charging, and so on and so forth, before returning back to the caller. So in summary, there are a lot of downstream calls happening for each request. And the challenge that I had was the integration with other services. Some of those services return in timely fashion, but most of them are not. And this was a big problem for me, simply because a bottleneck in one module will quickly build a high traffic in a matter of seconds. And the only way to fix this is to shut down the messaging gateway, process everything, and turn it on again, which was really bad for business because we closed the door. Right. And this is where I look for a better option, asynchronous communication. And fast forward a few weeks back when I built content for AWS Summit ASEAN this year, happening in May, titled Building Serverless Microservices, I realized that this problem still exists, that developers are still having problem with interaction between microservices. And yeah, I totally agree that asynchronous communication is definitely more complex than synchronous communication because there are so many moving parts. Right? And that's something I like to share for today. How you can implement asynchronous communication while reducing complexities with serverless for your microservices. So before we begin, let me introduce myself. My name is Donnie. I'm a senior developer advocate for AWS covering for ASEAN. And I started my professional experience as a software engineer, R&D manager for various industries, ranging from banking to telco. And I was CTO for several startups. I'm specialized in microservices, event-driven architecture, and machine learning, especially in reinforcement learning. So yeah, so if you have any questions about microservices or even reinforcement learning, feel free to drop me a message on LinkedIn and Twitter. All right, so let's get into it. Just a quick run through of the agenda today. Today we're going to talk about communication pattern for microservices, which is going to heavily around the asynchronous communication. Then I'm going to take this opportunity to introduce you to Amazon EvenBridge, one of the cool services from AWS that definitely critical when it comes to building microservices. And also I have a few demos coming up. And by the end of the session, you will understand a few things. First is the potential issue on solely relying in synchronous communication. Then we'll move forward on how we can re-architect our system and start to use asynchronous communication. And in order to do so, we're going to leverage on Amazon EvenBridge as Event Bus to get our system more resilient and scalable. So yeah, so if you have any questions, please post it on Slido. This is the Slido link. There are two options on how that you can log into Slido. You can simply copy. You can I can pass it to you on the chat room. I think that's much better. Yep. Yeah. So you can just go to the link to. If you have any questions, or you can also input the event code serverless sg-async into the Slido application. Right, so I'm going to pause it for a while. Okay, so moving on. So as you might already know that microservices, it's getting more popularity since past few years. And done wrong, it will definitely damage the performance of your business. Done right, it will take your system to the next level. And one story that I can share with all of you is how Amazon, more than a decade ago, took the monolithic code base and broke it apart into service-oriented architecture. So they refactored their single code base into small, focused, single-purpose services, which they call as primitive. And this created a highly decoupled architecture where these services could be iterated on independently. And to give you an idea of the scope of these small services, I've included this graphic on the right. And that is the constellation of services that delivered the Amazon.com website back in 2009. And today, there are more of these across Amazon. And to me, this is just a perfect illustration because one of the challenges in microservices is how we architect the communication. Because really, when it comes to microservices, communication is the key. And this constellation shows us how important it is. Okay, so and then let's fast forward. Let me take you to imagine that we are building microservices. So let's assume that we are building an e-commerce application. We have order service to process service and invoice service to handle payment from our users. We have fulfillment service to get our customers' orders delivered to their doors, and also forecasting service to give help to finance and accounting department to perform some supply chain management and finance activities. So this is a really standard architecture. It's a synchronous API-based service. In this case, when a client makes a request to the order service, it has to make a downstream request to the invoice service, fulfillment service, and also forecasting service. And once it gets a successful response from all of them, it can respond back to the client with a success message, providing a confirmation number for the customers. And everything works well in this case. And over time, definitely there are more features to implement. And the order service might need to call more downstream calls. And this is totally normal. As what we know, as our system grow, we need to add more features and the data flow is totally unexpected. But what is problematic about having a synchronous API design is that the order service needs to get all record information from other services. So the order service needs to call all of these downstream requests before returning back the response to the user. And what happens if one of these downstream services has a hiccup? Well, in the worst case, we get our system acts really slow and will return timeout error to the caller. And even if we have implemented this system as a microservices, it still poses a few challenges. So one of the solutions probably like we can do like a vertical scaling. So why don't we do vertical scaling then? That's one of the probable workaround. But over the longer term, we might need to add more and more services to process the data, lookup query, update stocks, send to other third-party services, sending to data warehouse. And each time that order service needs to do that, it is highly coupled to the other services. It really making a potential bottleneck in the long run. So in the diagram, we have an order service serving requests via HTTP API. And to complete a request, the order service needs to make a downstream calls to 3 services, right? There are invoice service, fulfillment service, and forecasting service. And once that the order service receives response from all services, it will return back the response to the client. So we're going to use Amazon API Gateway and AWS Lambda for this demo. And there are 2 scenarios in this demo. The first scenario is the ideal scenario with the client calling the order service via HTTP API, and all downstream requests made by order service got 200 OK response, that's a HTTP status, from other services. And in this scenario, is going to be like a really ideal scenario if everything was fine. So in the second scenario, I'm going to change the timeout to 30 seconds to illustrate that some of the services take a longer time to finish. And we'll see what will happen. Okay, so let's switch to the demo. Okay, first, let me show you how the AWS Lambda functions look like. Okay, so this is the order service. It's a pretty basic function, and you can see that from this Lambda function, it's going to invoke other 3 downstream services before getting back the response to the client. So, right? So this is the invoke function routines that is going to call invoice service, fulfillment service, and also forecasting service, right? And this order service is actually integrated with Amazon API Gateway. So if we click into this this area, you can see the details of here, right? Okay, so now we have covered the order service. Now let's take a look into the other Lambda function. Right, so this is the forecasting service Lambda function. Nothing special here, but you can see that we have the timer, right? We have this time here, which we're going to use for the next scenario. Okay, now let's test it out. Okay, if I hit this endpoint, if I hit this endpoint, it will return to us all the response from other services. We have invoice service, fulfillment service, and also forecasting service, right? So everything is good. Right? And then if we try to hit this endpoint to simulate the traffic, I'm going to use artillery tool. I'm going to copy this link. Okay, so is it too small for the terminal? Do you need me to enlarge the font? All good?
I think slightly.
Oh, okay.
Yeah, it's a bit smaller font.
How about now?
Looks almost there, maybe a bit more.
Almost there, okay.
Yeah, looks good now.
Okay, cool. Yeah. Thank you, Harpreet. Okay, so what I'm going to do now, what I'm going to do now, I'm going to use artillery tool to simulate the traffic, right? So I'm going to, oops. Yeah, and then I'm going to do like probably 100 requests. Sounds good, right? And then I'm just hit enter, right? So we're going to wait for a while. See that we get all those requests with HTTP status code 200. And this means that everything was fine. Everyone is happy. But now for the second scenario, we're going to add some changes in one of the function. Now, the idea is to illustrate what happens if one service fails to complete requests in a systematic synchronous API design. So let's go to the, let's take one, how about, forecasting service. Right. So let's assume that the forecasting service needs to process a really complex scenario and it takes 30 seconds in average to complete a single request. So I'm going to change this value from 0, right, to 30, right? And then I'm going to deploy. So the endpoint and also this system is going to use the latest version. Right. Okay, so now let's try to simulate again the traffic with the artillery tool. Right, so I'm going to clear this up and we're going to hit the endpoint with the lower number of requests. Let's say like a 10 requests. Yeah. Right. And let's see what's going to happen. This is the awkward silence, everyone, when it comes to the live demo. Okay, so we now we see the artillery tools is still trying to hit the endpoint. Right, so we have the status now. We have 504. It's a 504 status code, which means the request is timeout. Right, and this is a classic challenge is in a systematic synchronous API design. And yes, you can do vertical scaling and increasing timeout in API gateway, but that doesn't solve the underlying problem. It's the design. And in this case, all requests that we just made using the artillery tool, they fail. Right, so let's go back to the slide. So what do we need to do to solve this challenge, right? And now we're talking about asynchronous communication. So instead of having order service to call each downstream services, it's now sending an event. For example, in this case, an order was created, right? And we have other services to subscribe to this particular event. Maybe not all services interested on taking any action to particular event. Maybe only 1 or 2 services. But with this kind of architecture, we are giving a freedom to our system for those services to act independently based on their task in serving requests. Now, with this architecture, we can decouple our system components and practically scale independently based on the demand. And the next question will be, how do we handle these events? So in this case, as a short answer, we need to have event routers. So introducing Amazon EvenBridge. Amazon EvenBridge removed the friction of writing point-to-point integration by letting you easily access changes in data that occur in both AWS and SaaS applications via a highly scalable central stream of events. Now, with EvenBridge, you can get a simple programming model where event publishers are decoupled from event subscriber, right? So this allows us to build a loosely coupled, independently scaled, and highly reusable event-driven application. It's fully managed, so it handles everything from event ingestion and delivery to security, authorization, and error handling, making it easy to build scalable event-driven application. And one more thing, because EvenBridge is serverless, that means there is no infrastructure to manage, and you only pay for the events that you consume. And this is one of the common feedback that I get from developers when to choose AWS services to build the event routers. And Amazon EvenBridge is a significant addition to AWS offerings on building event-driven architecture, giving you freedom to choose the best tool in your case. Now, there are two main types of routers used in event-driven architecture. There are event buses and event topics. You can use Amazon EvenBridge to build event buses, and you can use Amazon Simple Notification Service or SNS to build event topics. And you can integrate Amazon SNS and Amazon SKS to build a powerful PubSub. Now, to distinguish when to use EvenBridge and SNS, let me help you with this simple guidance. So Amazon EvenBridge is recommended when you want to build an application that reacts to events from SaaS applications, AWS services, or custom application. And Amazon SNS is recommended when you want to build an application that reacts to high throughput and low latency events. And with Amazon EvenBridge, it actually uses a predefined schema for events, and it helps you to select and filter those events. While for the SNS, the topics are agnostic to the event schema. Right? So I hope it helps. Right, so let's take a look at how EvenBridge works. So it all starts with an event source. This can be any of AWS services, your custom application or SaaS application. And when you use a SaaS application integration, there's a special resource called a partner event source that provides a logical connection between the partner system and your AWS account. Now, here's the magic. Without the need for provisioning and managing cross-account IAM roles or credentials. Now, once that you have this an event bus, you can associate rules with it. Rules allow you to match against values in the metadata and payloads of the events ingested and determine which event should get routed to which destination. And I mentioned this earlier and just want to iterate again that by using Amazon EvenBridge, we can expand event sources. And that's not limited only to AWS services, but it could also having third-party integration. So with EvenBridge, you can easily integrate your application. For example, for SaaS application like Zendesk, Datadog, MongoDB, Sugar CRM, Auth0, and Segment, and many more. You can see all the lists in the EvenBridge dashboard. And with this kind of integration, it makes more easy and seamless for us developers to subscribe to standard third-party events that we might already use. Okay, so another demo. In the next demo, I'm going to show you how Amazon EvenBridge can solve this systematic synchronous API design challenge by changing the architecture with leveraging the EvenBridge as an event router to handle the asynchronous communication between services. Okay, so this is how it looks like. Whenever order service receive requests, it's going to publish an event called order created to EvenBridge. And then Amazon EvenBridge will then push the event to respective services which are being the target for the particular event. And in addition, few of these services will publish their own event. And so EvenBridge will handle and push the event to the target services as well. Additional event that I'm going to create in this system is the fulfillment completed by fulfillment service, which will be consumed by a logistics service. Okay. I hope you understand the event flow for this system. So the idea is to have a complete data flow whenever the system receives order creation. And there are 5 Lambda functions that I use for this demo. And these services used in this demo is to help to demonstrate how scalable and robust if we build a microservices with asynchronous communication and event router. So it's probably more complex compared to our previous demo, which is the systematic API design, but it surely helps us to scale. And one thing that I like to emphasize is none of these functions know the existence of each other and no link whatsoever. All the communications will go through EvenBridge as these functions publish their own events. Okay. All right. So let me switch to the demo. So yeah. So the second demo. Here's my mouse on this. Okay, so this is the EvenBridge console that you see that I have created an event router called Lab2CM Event Bus. Now, if we go to the rules, like you see there are 2 rules defined. Right? The first is the fulfillment completed, and the other one is the order created. And one of the most important components in EvenBridge is event pattern. And this is the fulfillment completed rule. So whenever it receives an event, it will match the event with the pattern that you have defined before routing the event to the target. So in this context, if the detail type contains fulfillment completed, it will go to the logistics service, which is exactly what we want to have. So the idea is like this: whenever the line items are fulfilled, it goes to logistics service to deliver them to customers. So if we go to the fulfillment function, yes, this is the fulfillment function, we can see that this function is actually published the fulfillment completed, right, to EvenBridge. There's no downstream calls to logistics service. It only publishes an event. And also in addition, it also saves the data to DynamoDB, which you can see in these lines. And all of these functions in this demo have the same functions to save to DynamoDB. Right. So I just want to emphasize that these lines is how you can publish event. It's really straightforward. You only need to call put event API and then fill the parameters such as source, detail type, and then also the event bus name. And this detail variable holds our payload. So your data will go there. And all of these parameters could be used when we want to define the rule in Amazon EvenBridge. Right. And I also have other Lambda functions that will produce and consume event for this demo. So you can see here that, and this is all of them. We have forecasting service, we have order service, we have invoice, fulfillment, and logistics service. All right, so let's test it out. We're going to change the timer. All right. Okay, so we have this time here. I just want to illustrate to simulate the fulfillment services. Takes time to complete one request, similar to our previous demo. So I'm going to put it here, and then I'm going to deploy this function. I think everything looks fine. Okay, so similarly to our previous demo, the flow is started whenever we hit an API request, and the order service is our public API and integrated with Amazon API Gateway. So if we open this link, right, it will give us, let me try to refresh. Okay, so it will give us an HTTP OK status code with message order created, and that's good. Now let's see the record in our database. This is our database, and then, oopsie, this is, let me check it. Order status, and then click the item. Okay, so let me try one more time. You can see that there's a missing here, right? So that's actually what is done with the timeout. So let me try to refresh it again, and then I'm going to refresh my DynamoDB. See, as you can see, we are missing 2 fields here: fulfillment service and invoice service. Fulfillment service needs 30 seconds to finish the request. That's why it's empty. And invoice service needs to wait for the event produced by the fulfillment service. Now let's wait for a while, for 30 seconds. of another awkward silence, right?
Yeah. I think meanwhile, if somebody has a question, please feel free to type at least. Yes.
Yes, please. I love questions. Is it 30 seconds already? Let me try to refresh it. You see? So as you can see that we have the record is now updated with timestamp for all services. So in summary, we can see that by using asynchronous communication, we can decouple all services using event router, in this case, Amazon EvenBridge, and we can independently scale each service and avoiding bottleneck in our system by relying in, really relying in synchronous communication, right? Okay, so let's switch to my slide. Okay, so we've seen how we can use EvenBridge to decouple our services, but there's a slightly problem here. And because all that we have done is actually architecting the communication for our backend. But as you know that most of the requests are being called by the client. It can be a web application or mobile application or even IoT devices. And this is the common question that I receive from developers that how can the external client get the response if the internal communication is happening asynchronously? And as an answer to this problem, there are actually a few things that you can do. The first one is to implement asynchronous request reply pattern. Second, using Websocket for communication between client and server. And lastly, using webhook. And in this session, I'm going to cover the first two, asynchronous request reply and also WebSocket. So the first one is asynchronous request reply pattern. So this is actually a classic pattern, and there are more than one way to implement this pattern. I used to use Redis or Memcase, but now I prefer to use DynamoDB with TTL because it's serverless, right? And the way this pattern works is like this. First, the client makes a request to a specific endpoint to request backend to do something. Next, the request goes through an API gateway, and the Lambda function will receive the request. It will then store the request into DynamoDB. It will create a request ID with TTL, preferably. And meanwhile, it will also dispatch an event to the Amazon EvenBridge. And just like we already discussed in previous demo, right? So we're not going to cover that. And then the Lambda function will return the request ID back to the client along with the HTTP status 202, which means the request is accepted, right? And now along with the response, it could also include the endpoint for status checking or to get the response from. Now, here what makes it really intriguing. While the backend processes the request asynchronously, the client will need to do HTTP polling. It can be for every minute, for every 10 seconds, and it will trigger to the specific endpoint to check the status of the request. Is it done yet? Is it done yet? Is it done yet? It's going to do something like that in extended period of time. And if the request is already done, it will then trigger another endpoint to get the response and passing the request ID. Otherwise, it will keep on polling. And you can also persist the request to Amazon S3, but I found that this method is really simple to implement. Now, the other solution, which is, in my opinion, is more elegant and modern, is WebSocket. So WebSocket, unlike a REST API, which receives and responds to requests, a WebSocket API supports two-way communication, full duplex, between client apps and your backend. Now, the cool thing about WebSocket is that the backend can send message to connected clients, and that even with the client requesting any calls to the backend, and making WebSocket a very popular method to deliver real-time updates between client and server. And building and deploying WebSocket is a fairly easy thing to do. You can quickly build one with various languages like WebSocket package in Go or Python. The problem is maintaining and operating the WebSockets. And fortunately, you can use Amazon API Gateway to deploy WebSocket. So a WebSocket API in API Gateway is a collection of WebSocket routes, and they are integrated with backend HTTP endpoints like Lambda function. So if you're building with Amazon API Gateway in your WebSocket API, the incoming JSON messages are directed to backend integrations based on routes that you configure. And one of the important concepts is route and a route key. And just want to give you a quick overview. There are 3 predefined routes in Amazon API Gateway WebSocket API that you can use. It's connect, disconnect, and default. In addition, you can also create custom routes. And route key is the value that is expected once a route selection expression is evaluated. Right. Let's look into another demo on how we can use WebSocket and Amazon API Gateway. Okay, so for this demo, I'm going to use our previous demo on choreography, which is the second demo. And I've added the WebSocket in the Amazon API Gateway. I think I have the slide over here. Yeah, so this is the diagram that we use for the second demo. But in addition, I have already implemented the WebSocket API in Amazon API Gateway. So our microservices can communicate back to the client, right? So this is the Amazon API Gateway dashboard. And here that I've mentioned, there are 3 routes, predefined routes available. That is connect, disconnect, and request. So connect, disconnect, and also you can also create your custom routes. And here I have the connect route integrated with AWS Lambda function, right? Yeah, so each route is integrated with the Lambda functions to handle a specific task. Right, so I just want to give you a sneak peek on how it looks like. All right, so let's test this demo. Oh, I haven't got the server. Okay, so just bear with me. I'm going to start the server first. This is the WebSocket backend status. Okay, and then I have this web. Oops. So what I'm going to do is I'm going to start the dashboard, which is actually a simple web page, but it's running on my remote development machine. Okay, so now it's running. And then I need to create a tunnel. My local machine to the remote development. All right, so let's try to reload this. Oh, good. So, yeah, so this is our dashboard. And nothing too fancy over here. It's just to give us an info from our backend. So the idea is like this. When our microservices complete something, it's going to update this dashboard, right? And just to recall, whenever we make an API call to order service endpoint, the order service will publish an event to invoice service, so it could send the invoice to the customers. And the event that the order service publishes, it will also be consumed by the fulfillment service. Now, remember that the fulfillment service takes a bit of time, around 30 seconds to complete the request, right? And once it completes the request, it's going to publish another event, which is logistic started, and it will be consumed by the logistic service. And each of the status of each service is going to be updated on this dashboard. Right, so now I've opened the inspect tool here, right? So if we go to this network tab, you can see that it's actually already established a connection, a WebSocket communication with API Gateway. And this will be the primary transfer for communication for this demo, okay? Cool, so let's use artillery tool again to create, how many? Like 100 requests. I'm going to copy and paste this one, this link, and then yeah, probably 200. Let's pick 200. Okay, so, what's going to do, the artillery tool is sending a message, and the dashboard is actually receiving messages. And now the order service is now updating, or it's already updated, and invoice service is being called. And the fulfillment completed is trying to finish the task, and you notice that once the fulfillment completed is done, it's going to ship to the customers, right? And you can see that from this for this debugger for this inspect tool, you can see that there's a lot of messages coming from the WebSocket, right? And that's how we use WebSocket for a full duplex communication between client and server, right? Okay. Oh, right. So before we do Q&A, just a gentle reminder that the AWS Summit Online ASEAN is coming in May 18. I need to fix this. May 18 and 19. And I highly recommend you to join this 2 days event. And best of all, it's free. And I'll be speaking in Summit event, presenting a session titled Building Serverless Microservices. This is going to be a level 200 session and above, as I focus more on various design patterns for microservices like log aggregation, API gateway pattern, and event replay, and how to implement those patterns with AWS. So please join me in the session. And if you do, please say hi on the chat. And I also deliver 2 other sessions in reinforcement learning and AWS, AWS Deep Racer, level 300 and 400, and it's tailored for those who love to tweak their Deep Racer models. Okay, so and also some of the demos that I presented today are part of the event-driven microservices workshop that I published on GitHub. So this workshop is intended for you who want to deep dive into event-driven architecture with AWS. It's free, obviously, and it has 3 labs from producing and consuming the event to do choreography and lastly orchestration with step function. Everything comes with CDK and detailed instructions. So if you want to try it out, please do, and hoping you can give stars and feedback to help me to improve the content. All right. Okay, so Q&A time.